So let's change this. Oh yeah, no problem. What about the question from 1.1 that you noticed? Oh man, I have not gone back to that. I'm so sorry. That you noticed was right. We'll have to return to that. Yeah, what one? Which one was that? What did I say I needed to do about it? I don't remember. I just remember the fact that you brought it up. Like, what did I say I was gonna do? Or what did I say I needed to do? Did we remember? It was 13. And I said did I say that I was gonna go and like redo it, or did I have to go and like message them or something like that? That's what I'm asking. Oh, okay, let me just quickly do that right now. Is this 13 from 1.1? Okay, cool. I'm just gonna quickly just open it over here. And click on it. Okay, and I'll leave this open to deal with later. Does that sound cool? And then I'll message them. Okay. Awesome. So let's change this. Cool. There we go. Okay, so today we're going to keep going forward, and this is about polar coordinates. But now, so remember how before we did integrals and we were able to find like the length of a parametric curve, the area under a parametric curve, and all that sort of stuff? So we moved from rectangular coordinates to parametric equations. And then last class, I think that we ended with talking about polar coordinates, period. So today we're going to talk about like, well, what happens if you want to integrate using polar coordinates? So just a quick reminder of how of these coordinates. Sorry, I'm like readjusting my screen. There we go. My book keeps on flapping open. It's annoying me. Okay, so zoom. Sorry. Come on, zoom in more. Come on, zoom. Oh my god. Thank you. There we go. So we learned that, what were the two variables that you use in polar coordinates? There we go. Let's just start from there. Let's see if people remember. What are they called? Thank you. So we've got r, we've got theta, and the way you should think about it is, let's say that we're drawing this on rectangular coordinates. If you have some point, let's come up with this point right here. We'll call it, actually, let's change that. Let's have it be blue. Let's say this point is 3 comma pi over 4. So that's in that's in polar coordinates. So you have to remember that the r value is how far you are from the origin, right? So you can think of it as like a radius. So distance from the origin is r. And then the theta is how you rotate your angle from the x-axis, and we always rotate in a counterclockwise direction, right? So, you start at 0, 0, r is 3, so you go out to 3, 0, and then you rotate that angle up to here. Okay, and we found out that there were some ways to translate between polar and rectangular coordinates. For instance, we know that if you have polar coordinates, you can get the x and y values pretty straightforward. It's r cosine theta or r sine theta. Okay, and then if you want to go the other way around, r squared equals x squared plus y squared. And we know that theta equals the tangent of y. Wait, is wrong. We know theta, theta equals the tangent of y over x. Cool. So you can think of these as in pairs to help you translate between them. When I wrote this last time, I think I took the square root of both sides of the r squared equation, and I think I wrote the theta equation in terms of like tan inverse, but I mean, it's the same thing. Okay. So hopefully this is ringing a bell. So what we're interested in today is regions. Let's try to type this down. We are interested in areas of regions bounded by polar curves. It's like, what does that even mean? Change that to heading 2. So let's say you have some polar curve. So for polar equations, you get r equals f. So you remember the way it works with polar equations is that you always define what r is. Okay, and then so you're gonna have some function and it's gonna be defined by some angle. So like as an example, I think like the example I gave you last time was like, what if r is equal to 4 sine theta? Notice that the r variable is given in terms of the angle. So theta is theta is the parameter or the independent variable. So notice that theta is the independent variable or parameter. So in other words, you plug in theta values to figure out how far the point is from the origin, right? As the way you can think about it is, as your angle is changing, you're wondering, like you choose some pi over 2, how far out should my point go? If you're choosing pi over 4, how far out should my point go? That's the independent variable. You can think of it as you're like sweeping around. Okay. So for how we're going to do this, we're going to say, so remember how for parametric equations, our parameter was t, and then you would always define what the bounds in the parameter are. So for us, we're going to say that theta is between the values alpha and beta. So in other words, for the graph that you're looking at, you're only interested in the theta values between alpha to beta. There might be more you could plug in, but that's what we're interested in. Okay, questions so far? Sorry, I'm like stretching. How are we feeling? Let's get some reactions. Like, making sense? This should feel very similar to parametric equations. Just you're using different variables now. Okay, cool. Okay, so what we have going on here is, let's just sort of draw this. You have, let's put in the x and y axis. Come on, where'd you go? There you go. So you have some curve. Let's just say the curve looks like this. So this here is the graph of r equals f of theta. And you're interested in the graph between theta equals alpha theta equals beta. So remember that when we were dealing with in rectangular coordinates, the situation was similar but different. Oops, I do not want this. This isn't green, that's ugly. 1 second. Let me draw this before I say anything. So this could be my f of x. And for rectangular coordinates, you would be interested in the area between x equals a and x equals b, which would be like this stuff. Do you see how I don't have vertical lines anymore for this example? Why do these green lines here, why are they going like this? Why don't they look like the case over here, where between x equals a and b is vertical lines? Like, why do we not do it like this? It's a good question. Sure. So let me undo. So notice, like, when you're looking at rectangular coordinates, you're looking at the area under f of x. Do you see how x equals a and x equals b are vertical lines? And you want the area under f of x between x equals a and x equals b. Whereas over here, the area I'm interested in is this stuff. Why are theta equals a and theta equals b not vertical lines or line segments? Like, why does it look like Mr. Pac-Man is taking a bite out of something? Roger, yeah? On the left-hand side, we are in polar coordinates. And our independent variable or parameter variable, theta, means an angle. So when you're talking about being between theta equals a and theta equals b, you're between this angle and yeah. But you're basically saying it. But I was like, wait. The words are like switched. What you're saying. So like on the left hand side, we're in polar coordinates. Theta is an angle, so that's why we're between this angle and that angle. On the right hand side, f of x is rectangular coordinates, so we're between a vertical line x equals a and a vertical line x equals b. So this sort of throws people off sometimes, but I'm curious if the difference between them makes sense when I put it that way. Here we're dealing in polar coordinates r theta. Here we're dealing in x and y coordinates, or rectangular coordinates. So x equals a is a vertical line, whereas over here, theta equals alpha is, you can think of it like as an angle. So you get this like little line that, along some angle from the x-axis. So I'm going to pause. Does this idea make sense? Okay. Let's activate our knowledge a little. On the right-hand side, what is the method that we use for calculating, or how do you end up calculating this area over here on the right-hand side? So you have this area. Like, ultimately, how do you end up figuring out what that area is equal to? Okay, cool. Now, how does integration work? Like, practically speaking. Okay, wrong question. I guess what I'm saying is, like, if you didn't know any integration formulas, what would you have to do? That's the better way of asking it. Yeah. So, cool. So, on the right-hand side, if you would have to be like, okay, this integral from a to b, f of x dx is actually equal to the limit as n goes to infinity of sigma I equals 1 to n of f of x delta x, right? Do we all remember this, like from forever ago? So, I don't know who said that, but they're right. Like, you're gonna sum up some rectangles. So, what is this delta x in the formula? Actually, it's not the number of rectangles, that's n, interestingly enough. But it's really related to that. It is dx, but what does it practically mean when you talk about the rectangles? Yeah, it's the width of the rectangles. That's basically what you're sort of saying there. Like, really close. So let's change my color. So like you're gonna like add together some rectangles, right? The heights will be determined by the function. So I'm like drawing them in, what's it called here? Orange. And delta x is how wide each of these things is. Do you remember what the formula for delta x is? Because each of the rectangles has to be the same width. Anyone remember? So close, b minus a over n, but like basically good enough. Yeah, you said a minus b, but I mean, like, it basically counts. Do you know what I mean? I'm like, whatever. You flipped the two numbers, good enough. Yeah, you're like, oh, why did I say it like that? So what you do is because b minus a is how wide it is from a to b. In other words, from here all the way over to there. So you're taking your thing from a to b and you're splitting it up into n equal parts. Okay, the question now is, how do you find the area over on the left-hand side? And what you're gonna do is something super similar, but instead of using rectangles, you're gonna use things that sort of look like cones. You're gonna go, oops, what the? Okay, I messed that up. That's not how that was supposed to look. Yeah, slice is the better term because cones are 3D. I was like, that was the best shape I could think of. So what you're gonna have is, let me do this in a slightly different color. You're gonna go from here, and it's gonna have like a flat top, and you're gonna get I guess, what should we call this? What shape is this? It's like a pizza slice. Does everyone see like my little pizza slice right there? So sort of like how you have rectangles under the curve, I'm gonna have these like little pizza slices, they're little triangles, and I'm gonna add those together. So let me like draw another one. So you're gonna have one that looks like this. And then you're gonna have one that looks like this. Okay, and these pizza slices, or whatever you want to call them, are the equivalent of the rectangles. So if we want to find that area, we're going to do that. And what you notice is that these little pizza slices, they split up my angle into, do you see 3 equal parts? So instead of having delta x like we have on the right, we're going to have delta theta. And delta theta is equal to beta minus alpha over n. We're splitting up my angle between theta, or alpha and beta, into n equal parts. That's why you get those like 3 pizza slices if n was 3. Okay, so are we getting the connection there between the two of them? Just like how you have the rectangles and the rectangles are the same widths, now you get these like pizza slices, and they all have the angle split up into equal amounts. Yeah. Cool. Now, on the right-hand side, you need the area of these rectangles, so we know what delta x is. What else do you need to know about the rectangles to figure out their area other than delta x? Okay, we need that, but also something else. Let's say you have 10 rectangles. You know that they're all with delta x. What else do you need to know about the rectangles to figure out their areas? Yes, you need the heights. That's the f of x in this formula right here, which I just underlined in blue. Okay, and then you need a formula to plug in to them. Remember like how you choose like the left endpoint or the right endpoint? So like in 101b or the end of 101a, you learned that like there's this formula xi, which is like a plus delta xi minus 1 to figure out those values to plug into the function to determine the heights. There's a super similar thing for polar coordinates. Your formula quite simply is theta I equals alpha plus delta theta I minus 1, just like this one over here. But instead of using x values, you're using theta values. So what this gives you is like, if this is your r equals f of theta curve, this would be like your theta 1. This would be like your theta 2. That would be like your theta 3. And then what you would use is like these values to actually like make the heights for your little pizza slices. And then that would give you the area you're trying to estimate under them. And then you would like keep going. And that's just like the equivalent of the rectangles on the other side. Orange writing where? This one? That one? That's an A. Right hand side is A and B. Left hand side is alpha and beta. Alpha and beta refer to angles, A and B refer to x values. See, there's like a clear distinction between these. That's why we use completely different letters so that you know which side you're dealing with. A and B for rectangular coordinates, alpha and beta for polar coordinates. What time did we go until? Okay, we're just gonna end here. We're gonna pick up with this tomorrow because there's still more to do. We're gonna like have to put all of this together. Eventually, what we're gonna do tomorrow is like, you know how here we have like this definite integral equals to this Riemann sum? We're gonna figure out what that has to be for polar coordinates. So we're gonna come up with the equivalent of this thing for polar coordinates. It'll be cool, but like we can't do that in 5 minutes. So does that make sense? Because we're not gonna be able to do it, might as well just end early. Like there's no point in like doing the rest. Like we have it set up, we see how they're similar. We're gonna pick up from here tomorrow and like figure out like, oh, so what does the new one look like? Okay, so before you go, please say I was here in the chat.